We'd like to start the WPI seminar. So today we have Professor Françoise Winnik from University of Montreal, and now she is also appointed as a PI of polymers, and also affiliation is also University of Helsinki. And she's a kind of a special guest for this I²CNER seminar. And you can find her CV in this poster here. And we do not need any. I think I do not need to explain detail because her activity is very famous in the field of the physical chemistry of surface and interfaces. So now she is also a chief editor-in-chief of Mirror. And today she is going to give a talk on Tailor-cut polymer colloids and the interfaces from design to application. So let's welcome Professor Winnik.
Anyway, thank you very much for letting us. Do you know what I have to do here? Somebody started this thing, and this is okay. So the title actually is sorry, number one. No, can you hear me at the back? Okay. The title, I should have been here at least 6 months ago. I was invited, everything was sent, and then a typhoon decided to come just about the same time as me, so I was too small to fight. So the title, we'll see, since then I've changed a little bit what I was doing, and my title is a bit off. So first, I would like to briefly tell you a bit about my history, and so you understand better what I'm doing. And also it's for the young people amongst you. You know, I always think when I graduate, I'm going to work in this company and I'll be there until I'm 65 or whatever. This is all wrong, you know. What is really nice when you're into science is that you can go this way, that way, and there are always new avenues open for you. So I didn't think that I would end up being like this, but through history, through people I meet, I changed to many places. So I'm right now at the University of Montreal, so Montreal is here. So it's towards the east of Canada, but it's still not at the Prince Edward Island, for example, we down here, which is much further east. So University of Montreal is here, Toronto. This is in Alberta, where they have a lot of oil. Used to be very rich, now all of a sudden their pockets are empty because the oil price is down. And Victoria and Vancouver are here. That's British Columbia. So personally, I am French. So I was educated in France. I get a chemical engineering degree. After this, I decided to go to Canada to learn English and do science at the same time. And I did a PhD in organic chemistry and photochemistry and postdoc in medical genetics. So already I was wishy-washy what I wanted to do. And then I worked for 12 years as an industrial scientist for the Xerox Corporation in Canada. They had a research lab. And I think coming back to my own career, I find that this was a very, very important time in my career, because I started as an organic chemist, and I felt that making molecules was the best that a chemist can ever do, as all organic synthetic chemists believe. And I realized that when I was at Xerox, I had to collaborate with physicists, with polymer scientists, and slowly I became converted into someone who looks at polymers and at interfaces and uses chemistry when you need it, but not as an end, synthetic chemistry. So after going to Xerox for 12 years, I decided, well, academy is for me. And I went first to McMaster University, which is between Toronto and Niagara Falls. And it was in the chemistry and physics department at the time. And finally, I went to the University of Montreal, and there in chemistry and pharmacy. So I am quite omnivalent. Since 2011, I became a principal investigator in MANA, so it's a satellite lab in Montreal. And I'm also a distinguished professor in Helsinki. I've always had close connection with Helsinki. So, this is the campus in Montreal, and this is our building. It's called Bombardier, which is who is the constructor of small airplanes and trains, who you know about it. So we give money to the university. This is inside the building. It's very airy. It's quite beautiful. It's located here. This is the main campus, the old campus with a big tower here of the university, a big park here, and on this side you will see a cemetery, a very famous cemetery where many famous people are buried. This is the stadium that was built for the Olympic Games in Montreal a long time ago, so it's still on. And I do a lot of work, or I did more in the past with the Institute, the Art Institute in Montreal, which is quite a big center. So I'm actually delocalized in 3 different labs in Montreal, Helsinki, and Mana. And my colleagues always tease me and say that the sun never sets on Winnik's empire, because I cover the whole thing here. So in Montreal, I work with responsive materials, drug delivery. We did a lot of polyelectrolyte multi-layers and used them on cells, to drug delivery. We are always also some of the first to do the folate targeted gene delivery. And this was done in collaboration with an orthopedic surgeon. So we do various things. And together with a colleague in pharmacology of my dear Dr. Messinger, we studied a lot on the toxicity of quantum dots. In Helsinki, I work on responsive materials with Tenhu, and we also started a big project, and this is actually why I am this Finnish distinguished, on drug delivery for the eye, for diseases of the eye. Finally, in Mana, I can see some of you are getting bored. I work also on responsive material for cardiovascular. I'll talk to you a little bit about this. With Goldberg's son, I work on boron nitride nanotubes. We do nanoarchitectonics. We try to understand what there is, because this is the whole purpose of the center. And more recently, I started to work on aggregates of cells. And I decided I would talk to you about this, because it's something that has to do with colloids, but it's kind of removed. I mean, aggregates are aggregates, but they are cellular aggregates as opposed to particle aggregates. So, self-assembly occurs in many different forms, which I've drawn here. And so I talk to you today about aggregates, about colloids, and about fields as well, on interfaces. So, the first topic is to do with fields. So this is something related to what's happening here, has to do with the zwitterions. And probably you know chitin. It's a natural polymer which is extracted from shellfish. I mean, we have a lot of lobster in Quebec, so it's kind of one of our natural resources. We can, the chitin itself is totally insoluble in water, but if you remove the acetate here and replace a lot of them with the amine, it becomes soluble in acidic medium, but not really in water. So it is though a natural polymer, it's quite biocompatible, it's degradable. So it's very useful, except that it's not very easy to use it at pH 7.4, which is the pH of our body. So if you want to use it for biomedical application, you first have to dissolve it in acid, and then try to move the pH up to neutral and make sure it's still soluble, which is not exactly easy. So many people are trying to modify it, and we succeeded in introducing the phosphoryl group, which is non-fouling and very good for the biomedical application. And also, when we convert some of these amines from primary to secondary, we introduce this group, and it becomes quite soluble in water at normal pH. So this is, of course, because we now have this shell of phosphoryl, and we use it, for example, the polymers to form multi-layers with polyanions. And we actually used it also to cover red blood cells to make them more immunocompatible. So this was some work done by Dr. Montreal. Now she was a really brilliant student in my group. I won't talk about this today. This is all stuff. But now, if you consider this polymer from a point of view of a cell, you have on one side chitosan itself is known as a very bioadhesive polymer, which means that the cells like to adhere to it. On the other hand, the phosphoryl is cell repellent and protein repellent. So suppose you put a cell on a film made out of this polymer, what is it going to do? Is it going to be to absorb, or is it going to be repelled? You know, we give him a double message. So we did first to prepare the film, and we then checked the absorption of fibrinogen, which is one of the proteins which is important in the adhesion of cells on a substrate. And we noticed that as the content of phosphoryl increases from 10 to 40%, the surface becomes first protein adhesive and then protein repellent. This is from a QCM scan. So what the cells do? Cells tend to, depending on the amount of phosphoryl on the interface, if they sense that there are a lot, the cells don't like it, so they don't want to adhere, and they tend to aggregate. So if you try to culture cells on a surface with many phosphoryl here, the cells tend to form aggregates. They don't spread, they prefer to have contact with each other. So if you now look at, these are the same cells, they're Hubeck cells, human umbilical vein, and endothelial cells. On chitosan, phosphoryl 15, 25, and 40%. And this is on polystyrene, so this is after 1 day, 4 days of culture. In the polystyrene, you may not see it very well, but they are really elongated, they are very heavy, they adhere. Whereas in the case of the CH2C film, in here they form little groups, you see, but they don't spread. And with 25, they form really aggregates, and these are aggregates that are being formed. So we can see that this surface is really more cell repellent. It doesn't, the cells do not like to adhere. So we collaborated with the person in the cardiology department and also did a lot of work, and they showed that they are allowed to amplify and the progenitor cells, the stem cells, so they are using it for various applications in stem cells. We are not doing this, they are continuing, we are making the polymers for them. But what we have done recently is to use estradiol. Now, I don't know if estradiol, everybody knows it's a hormone, it's a very important one, and you may not, a fact that is not so well known is that estradiol is also very useful to prevent cardiovascular diseases and also to promote repair in the case of cardiovascular diseases, among many other phenomena which are not related to the genome. So we were working with a cardiologist and we were trying to make polymers that would act as a drug delivery system, where we would attach the estradiol to the polymer and possibly coat stents with them, for example, to have a surface that could release the estradiol once the surgeon put the stent on in a tube in the artery. So we made this polymer, and for example, in this case, we make one that has quite 20% phosphorylcholine and just about 4% of this estradiol. So we made it, and the key point you have to understand, and I'm going to do a little bit of cell biology with you, is that the estradiol has his hormonal effect. It needs to go to the nucleus to interact with the DNA. So it somehow gets transported through the cell membrane and forms a receptor, a complex with an estrogen receptor, and then goes into the nucleus, where it does its job. Now, the other effect, for example, the effect on the cardiovascular system, does not go through this mechanism. This mechanism takes a few days. The cardiovascular effect takes only a few minutes, up to an hour at the most, so they're completely different time scales. And also, there is very strong evidence that the non-genomic effect occurs on the cell membrane, so that the estradiol stays outside and does not penetrate. So it is kind of difficult to separate the two mechanisms, because if you put estradiol in a cell medium, it is not going to decide, okay, today I don't go in, I talk to this one only. So you have to somehow separate the non-genomic pathway from the genomic and prevent the estradiol to go in the cell. So this has been done by chemists who have attached the estradiol to a big macromolecules, to dendrimers or to proteins, assuming that the protein or the macromolecule is not going to be able through the cell due to its size and also the mechanism of cell internalization. And it worked to some extent, but also it was noticed that, for example, in the case of the dendrimer was also seen in a cell, so it's not clear. So I think to an audience like this one here, the obvious is to attach the estradiol to a surface, and then to put the cells on, and then the cell will be in contact with the estradiol, and the estradiol by no means will be able to go inside the cell. Okay? So this is what we decided to do. It was kind of an obvious thing to me as well. So what we did is we prepared again this estradiol, but linked to the cytosine. And we put the same amount, I think more or less, as before. And we made a film by first, the first time by spin coating. We dried it and then we rehydrated it to put the cells on it. So we did a spin coating and drying, and we form a film. And so we have the immobilized estradiol, it's arrow here, we have the phosphorylcholine cytosine and the substrate. So the first thing to do was to make sure that the estradiol would still be available to the surface. So we had a dried film at this point, and so it was easy, for example, to do some XPS. And we did the angular dependent XPS, and this is published actually. I think I showed you the paper. And so we could see that on the very top layer, depending on the angle you have, we have actually an enrichment in estradiol, which you could see by various bands here. Which we had, I think, done it carefully, and it was pretty clear that we had this. But the question then was, what happens when you rehydrate? I mean, you could kind of understand that when you dry the film, the estradiol, being very hydrophobic, would want to go towards the edge. But when we put it into water, where is the estradiol going to be? Okay, that was the next question. So we had to do the experiment, and we did it this way. Then we rehydrated it with phosphate buffer saline PPS. Or else we prepared the film wet and then washed the excess polymer away and then tested it. Okay? And we wanted to ask the question, are those two films the same, at least as far as cells will be concerned? Okay? So what we did with the instruments we had on hand is we did some QCM, post-crystal microbalance, which allows you to measure the thickness of films and the rheology of films as well. When you have the QCMD with dissipation, that gives you some feeling about the rheological properties. And we did two types of films. We prepared them inside, so they never went dry. So we just adsorbed the polymer. It was on, I think it was gold that we coated with a very short stier with a carboxyl, no, with an amine on the top surface. And we adsorbed the polymer, and we then studied the G prime, G double prime by QCM, got the thickness also. And we could see that the rheology in this case was an entangled polymer solution. And we could not really see the effect of E2. It was kind of very fluid. Whereas in the case of the polymer that had been dried and rehydrated, it really behaved like an entangled gel from the rheological point of view if you go through. This is the data extracted from the QCM, so I don't go through the actual raw data with you. And we could actually see that it behaved like a reversible cross-linked system, and we could sense we could determine or estimate the numbers of associated E2. So in this case, during the drying, some of the estradiol became really solidly associated. And the thickness, though, as determined by QCM, was approximately the same. So during the drying process, we feel that we had E2 were locked at the interface in half, and the whole gel was, connected by ion pairing as well as the estradiol. So, which was not exactly the message we wanted to have, because we were not sure that we had sufficient estradiol on the interface to actually have recognition, to have an actual feeling of the cell attached on it. So we didn't do the cell work immediately, but we did some interactions with the estradiol receptor. So you can actually isolate, and it's commercially available, the estrogen receptor, which is extracted from the cell. And we put this on top of the films, either air-dried and rehydrated or in situ. And in this case, when they were rehydrated, this is the raw QCM data. So these are nanomolar fields because of the receptor. You need extremely minute amounts of estradiol to trigger the response of the cell. So we could see that this was our starting point here. This is the change in the frequency during the QCM. As the frequency becomes more negative, it means that the vibration of the crystal is damped by the amount of polymers or protein that's absorbed. And after a wash with PBS, there is a clear significant shift in the frequency, which implies that the ER is actually adsorbed on the surface. Later on, we have done as well some cell culture on top of this film, and we could see that some of the biological signal due to the non-genomic effect could actually be seen on cells cultured on this estradiol film. So it is actually working to trigger the non-genomic effect of estradiol. So we see this, it could in principle be used to coat surfaces that you may implant later on to help the healing, but it's also a very nice way to actually test the genomic effect and try to understand it without interference with the genomic effect, because in this point that the estradiol is not going to be released. For those of you who are really keen chemists, you will see that structure I showed you, there is actually one ester bond. And this worried me from the day zero, because originally we wanted, these experiments, the original purpose of these molecules, polymers, were to be used as drug delivery. So we wanted to have it removed. At that time, that was maybe 5 years ago, I was working with a cardiologist, and he was not so, it wasn't so clear to him that or maybe to the scientists at the time, that the important thing was a non-genomic effect, which was only happening. It's a very controversial issue yet. So we did our work here, which I described, on this polymer. Since then, we have made a new polymer where we have no more such esters. So, and it works as well. So this was a minor thing that I thought somebody may see. So, but now we are working on a different synthetic. Okay, so these are the conclusions, right? So we are right now here, which because they are promising and there are many different approaches we could still use. And at this point, I'm going to switch to something totally different. So I don't know if you have some pressing questions you want to ask now. It's as you wish, because I'm going to switch, but we can come back later, whichever. So next, so this has something to, okay, I should go back just a few steps. I work at MANA, right, this Material Nanoarchitectonics Institute. And in order to trigger new ideas, new projects, the center sometimes calls for proposals. So there was a call for proposal just for the people inside. They just give you enough for a postdoc and some money. And you had to use experiment and theory. So any proposal that had some real good validity and that conjugated experiment and theory would be acceptable. So I'm the type of person a proposal is called, I'm going to write one, okay? And at this point, I had just done some work with my student, Bowen, who was actually in MANA for a while, and he had showed me the structure of those aggregated cells. Remember I showed that to you, the CHPC. And he's a good student, and he said, well, Dr. Winnik, look, they did it exactly. So he came with some papers, and there were theoretical papers, which were written by Françoise Brochard-Villard. I don't know, you know her? From Paris. I mean, she's a theoretician in soft matter physics. And she has written quite a few papers on the modelization of cells and cellular aggregate and cell physics based by analogy with the soft matter physics. So she actually is applying this theory to the way cells behave. So my student came to me and showed me all her recent papers. And somehow I knew her from her time where she was really working on soft matter physics per se, and had not really followed that, although I knew her very well. So when Bowen showed me the papers, I wrote to her. And I said, oh, I discovered your work. And then about the same time, we had this call for proposal. And I said, Françoise, shall we do it something together? And we wrote a proposal. And the proposal was somehow to model cellular aggregates. I'll come to that later. But you know, part of the deal was that I had to convince 4 or 5 people from MANA, who were part of the selection committee, that we were actually doing theory. You know, they were imagining theory like, you know, very, 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 very theoretical. And here was the theory of soft matter physics applied to cells. For them, this was not really theory. And I had to argue. I mean, you know, I had to really show that this was real true theory. And finally, we got it, okay? So we started to work with Françoise. And I think this is actually a slide I get from her. The more I think about the project, the more excited I become, because I don't know if you know what active matter is. It's actually one of those fields of science that has really come out only very recently. And it describes the way an ensemble of objects, of matter, behave. One example is, for example, the granular matter, which are like the sand here. You know, here it's very stiff, it's like a stone. But if you start to push it, all of a sudden it disappears, it starts to flow. Okay, so it's really active. You have here a fish or birds when they migrate. They move as ensemble, they move together. So this is an aggregate, if you want, of active matter. You can also have cells here. Here we have a cellular aggregate which will be aspired here in a pipette. And it moves through. It can behave as a solid or a fluid. These are ants. Ants also behave like this. So you have a whole many different fields come together to really understand how this active matter can work. So we saw here the aspiration. Now what Françoise did, and she's kind of become famous for it, is that she can see that entangled active matter, which is like those cellular aggregates, can actually behave like very simple liquid. So they can wet a surface, they can spread, and I'll show you some detail much later. Or they can also be very stiff and not be adhesive at all. So what we are going to try to see now is how when we add nanoparticles to cellular aggregates, we can actually see the motion and the activity of the ensemble. Now, if I come back to some real effects, cellular aggregates are often used as models for tumors because they are much more relevant to cancer than cell into leaf. Okay, usually when you test a drug, you test it on a cellular on a dish, okay, in 1 or 2 deep. And it is more relevant to use how a drug behaves with a cellular aggregate. So this is what we could see. You use a lot of nanoparticles for drug delivery. So is the fact that you have a nanoparticle interesting for the process or not? Is advantage inconvenient? So there could be some real important implications. So, cellular aggregates are used to make, in vitro, we see, for example, we hold different kinds of aggregates of cells and implants here, and he's having some black hair, this one a big ear, and it's kind of awful, but tissue engineering is a big thing in cellular aggregates. So the analogy we have between physics and theoretician and actually cellular aggregates, probably you know the idea of liquid wetting. So here when you put a liquid that wets a substrate, it flows, and here you are going to partial wetting. So the same really happens when you have cellular aggregates. The spreading parameter that you can define for a liquid can also be defined for cells. It's going to be the difference between the interaction, the adhesion energy of the cell to the substrate, and minus the adhesion energy of cell. And the cell substrate will depend on the substrate treatment or inhibited, whereas the cell will depend on some receptors on the cell. So I was thinking, when you have rice in Japan, the rice is usually quite sticky. If you want to make a nigiri, it sticks, right? Otherwise you cannot make one. So there is a strong rice adhesion energy, okay? Now if you are French and you cook rice, you do not want it to stick. I mean, this is a disaster. You have to have each grain well separated. And in this case, the rice aggregate is very, very small. Okay, you don't want to have an interaction. So cells don't use whatever rice uses. They use some receptors, and one class of receptors are called the cadherin. And we were lucky to have via Françoise and the Institut Curie in Paris in France, various cells with different expression of cadherin, of this receptor. So we can go from the sticky rice to the French rice, okay, very easily depending on the cell type. So depending on the cell substrate adhesion and the cell adhesion, you can have, the formation of really a two-dimensional gas. You see, when you put an aggregate here on a substrate, all around it you see a film of quite separated cells. So this is like a two-dimensional gas. Okay? When you go to a more cohesive cell here, you have actually a film. So it's like a liquid. And if you go to a very strong cell cohesion and mix substrate adhesion, you really form aggregates that don't flow. Okay, so you can see the similarity is real, and you can really actually apply this theory to actually model what's happening to an aggregate. This is again from Françoise, and it has been published. I give you the structure. So what we did, we had to do something new for our proposal. So we decided to see the interactions of cellular aggregates with nanoparticles, focusing on the mechanical and the rheological property of the aggregate. So we are not trying to figure out so much yet about the biochemistry of the cell or see if a drug interacts. We just wanted to see if an aggregate would change. Okay. Now there is some interest, and there have been examples, and I'll show you very few, where single cells that grow on a substrate very isolated were actually treated with the nanoparticles as well as 2D. Cellular aggregate, nobody yet has looked at it. So again, just a close-up on our aggregate because we're going to use them. So there are assembly of hundreds, thousands of cells that are about 500 microns in diameter. And they are actually trying to see that. So back to the nanoparticle. This is published by Kathleen Murphy in a nanoletter a few years ago. And she took cells and spread on top of it gold nanoparticles. And she observed that the motion of the cells was slowed down by the particles. Okay, she had several, both cancer cells and fibroblasts. She had several mechanisms, but it wasn't proven black and white why that was. But it was quite short. And then there was some other work also at the same time on 2D sheets, so with of cells. So these researchers put a substrate, and half of it was covered with a PDMS film, which we'll remove later. The cells were grown constantly up to here, and then they removed the PDMS film and watched how the cell would move. Okay, so this is a standard cell for cell motility. And if you look at the top here, this is the control. So this is the part that was covered with the PDMS, so the cells are here. And every time, this is 60 minutes to 40 minutes, you see the cell really invades the substrate, so they move reasonably fast. On the other hand, when we added silicon dioxide at 15 nanometers, the cells hardly move. Okay, this is shown here too. So again, there's a clear retardation. So they looked at the cells, there was no obvious cytotoxicity, but they see some microtubules which are important in the motion of cells that may be changed. But then here again, it's still quite unknown. Okay? So finally, I don't know if you have read about this, I don't think which kind of was interested, is from the group of Ludwig Leibler in Paris, and together with Letourneau also in Paris. They actually took made a wand in a tissue. Now here we do not talk about aggregates, we talk about real tissue, right? They took they did a wand and then just put a few drops of silica particles of 50 nanometers in diameter, and they found out that the nanoparticles really connect the cells back, so without any other thing, the wound was healed very rapidly. So their hypothesis was that the cells were actually like glue, okay? So it seems to be a very quick way and gentle way to heal a scar. Okay. So again, hypothesis the nanoparticles could glue the cell together. So what we decided we're going to test this. So this was one of our first experiments. We took, so how do you prepare aggregates? I showed you the thing where you see the cell moving together, but the actual professional way, or one of them that usually doesn't fail, is the pendant drop. Okay? So have you heard of this thing before? So what you do is you prepare a suspension of the cells in the cell medium. You put that drop on a cover of the petri dish, and then you turn it around, and the droplet kind of doesn't fall, it stays. And then gravity makes the cells go down here, and when they are close together, they tend to aggregate and form an aggregate. Okay? So in this experiment I'm going to describe to you first, we added nanoparticles in it, and we used cells that do not adhere. And we wanted to see if we could form aggregates in the presence of cells, okay? So we used those cells that do not have any receptor, and then later on I'll show you some that have. So we can have, if you look at when you put particles on an aggregate, they can be internalized, that's the first thing. They can act between and act as glue, and they may also interact with the substrate and then play a role. So right now we consider this. Okay, and using the pendant drop, we made aggregates first without any particles, and you see after 48 hours, there are a few aggregates formed, but if you shake them, they are very loose, they are not very good. Whereas with particles, we see after the same time really good aggregates. So in order to interpret all the results we got, we decided that we would do the following. We would count on each picture, I mean we did a lot of reading of micrographs, the number of groups. So a group was an ensemble of more than one cell. So we counted as a function of time the number of groups. And of course, with time you form more and more aggregates, so the number decreases. And this is the number without particles after 6 hours, and this is the number with particles. So there is a significant difference. So we form more aggregates in the presence of particles. And we define, so the number as a function of time depends on the probability of adhesion and on the rate of collision. Okay. So we then converted the data to what we call our factor J, which is the number of groups without nanoparticles and the number of groups with particles, with an infinite time will be equal to the adhesion probability with and without particles, the ratio of the two. And we can see that for a given particle we get some kind of limiting point. So this is the infinite time. And if we look now at this G and saturation as a function of various groups, the carboxylated polystyrene latex 2200, aminated 1000, we can see it takes a certain value, and the best number we have are with small nanoparticles. So when Leibler did his work on the glue, he used 50 nanometer silica. We show here that we didn't do this. We did actually the 15, so they are smaller silica, and they didn't work as well. But at least we have now a way to compare the glue capability of particles or cells. So we also noticed that in all cases, we had some time where nothing happened. And depending on the size of the particle, this latent time was kind of different. And that was very frustrating to the student who wanted to, the icon is not reliable. But we found out that this was actually due to the first step, which was internalization. And you can see that the cells are, the particles, they are fluorescing right here, they are internalized. So the first part here is internalization, and then we have particles inside and outside, and finally we have particles outside too. So at the beginning they can't really act as glue because they're internalized. So this is a summary. I don't know if I have more time because I think it's about 2 more minutes, or shall I mean how much? It's me, right? Should I continue quickly or very fast? Just a few more ideas about looking what's happening using this time adhesive cells. And so now the cells adhere together and we add the particles. And here, if all goes well, I shall be able to have a film the whole one. No, sorry. This I don't know how to do with this thing. How do I, no, you should. Here we go. Oh, no, it's done. You see, let's see, whoops. You can see that there is a film forming around here. You see the cells? You see, I don't know, okay? So here after the same time is 15 hours. Now if I do this with a function of the concentration, move as well, but the pure particle may move much further. So we have the field forms much bigger, so they spread much easier here. And then finally, when we even increase, so this is with higher concentration, they don't spread, they hardly spread anymore. Okay, so there is a clear way that when you have adhesive cells as well, we decrease the mobility. So this goes a little bit in the same way as, and we see that this is the speed of spreading, it really does go down with particle concentration. So, and now we are modeling this using the liquid spreading, and it's working extremely well. So this is finished, so I already had too much time. This is Françoise brochure. I don't know if any of you, she came to visit us. And these are the team that I have in my lab to do all the work. And this is my group in Montreal, whom I thank very much for all the help in all this. And they did all the work. And I thank you for your extended listening to me. Sorry.
Thank you.